All right, I don't have time to go into this in depth, but I did happen to gather some more baseball data before class here, looking at the difference between the performance of the American League Rookie of the Year in his rookie season versus his performance in the next season. The idea being to illustrate that the sophomore slump, so to speak, is a real phenomenon. Okay? Again, the basic reason is when they're a Rookie of the Year, they were both good and lucky, whereas in the next season, they're still good, but they probably weren't as lucky. Okay, and it's related to the fact that that regression line is underneath. It's got a smaller slope than the SD line. Question?
Just one comment on that too. I feel like the sophomore slump might not only be because they're not as lucky, it's just like when you see a player like do so well as freshman or freshman year, pitchers start to zero in on a guy too.
That's true too.
And not just chucking fastballs on the hill.
I think that's probably true, but at the same time, what I would be saying is, even if that weren't true, this still would be a phenomenon that happened. Anyway, I gathered data. I'll share this with you about various rookies of the year that were not pitchers actually, because you're all hitters. Highlighted Minnesota Twins in blue, Chuck Knoblauch, Manny Cordova, and just for fun. And you end up seeing that they're on OPS, which is their on-base average plus their slugging percentage. You don't need to worry about what that means. Was lower in their second season typically than in their first season. It's sort of an overall measure of how good they do at hitting and at getting walks as well. Anyway, we don't have time to go into that in more depth. I do want to go into more depth about the least squares line. Again, this formula for this thing called SSE, sum of squares of errors. Again, error is synonymous with residual, okay? Prediction error, that's a synonym with residual in the context of regression. So that's why it's called SSE. Another part of your electronic homework is going to be to fill in the rest of this table. I will again do it for the coffee. You will be doing it for the light absorbance relative to the nitrate level with this spreadsheet here, which I'll share with you. What's the goal here? The goal is to calculate the SSE. Notice SSE here. And put the answer there. I forgot to color that. Right there. Put the answer right there. That's what the SSE is. That's the goal. How do you do that? Well, you first have to calculate the y hat values, the predicted values. How do you do that? You use the given x values, these prices per pound, and plug them into the regression line equation to find the y hats. That's the goal. So you've got to use the slope and the intercept of the regression line down here. I could use those cell references and use dollar signs to use those fixed cell references, but I want to experiment with something. Well, okay, maybe I should go ahead and do that. I want to ultimately see why it's the smallest possible thing you can get. But anyway, here's how to do it. So I'm plugging those x values into the regression line in cell G4. That means I'm plugging B4 in. Meaning I've got to take the slope, which is in cell B16 here, use dollar signs, times x, which is in cell B4, don't use dollar signs for that one, and then add the intercept, which is in cell B17. Use dollar signs for that one. You know this is kind of small here. Squint, zoom in with the camera. In cell G4 here, I type equals $B $16, meaning I'm taking the slope, which is right there, times B4, that's the x value that I'm plugging in, 29, plus $B $17, that's the intercept right there. I don't use dollar signs for the B4 because I want that to get updated to B5 and B6 and B7 and B8 as I copy and paste. But I want the slope and intercept to stay the same. Do notice the intercept is negative, however I add it. The effect of that is to do a subtraction, but when you use the formula here, you've got to add it. Okay? You're adding a negative, that's the same as subtracting. Here we go. Should be close to this number, and yes, it's not too far away. This should now copy and paste correctly. Click and drag. All these numbers should be close to the corresponding y values over here, relatively speaking. Okay, they're not too far away. Those are the y-hats, the predictions you would get from the regression line. How do you now find the residuals or errors? Take the corresponding y values in cell C4 in this case, and subtract the predicted value you just found, in this case in cell G4. That's E, the residual. It's going in cell H4. Take the y value, that's the data value, minus the corresponding y hat value, the predicted value, for that value of x. But we can ignore x here. C4 minus G4 will calculate this residual. It is a negative number in this case because the data point is below the regression line. Y is below y hat. Click and drag this. Get a bunch of residuals. By the way, if you add up those residuals, you'll get 0. When you add up the residuals, you get 0. Now we want to square them. H4 squared will do it. You'll get the squared residuals. When you add up those squared residuals, you get SSE. This row is already a summation, so I can just copy and paste. Go over here. There's SSE, 0.301888. Okay? It turns out that if you modify the slope and intercept of your line a little bit, even a little bit, that number is guaranteed to get bigger, because that's the smallest it can be. That's what the regression line does, is it makes SSE as small as possible. That's why it's called least squares. You've minimized these squares, the sum of the squares of the errors. It will never go lower than this for this example, if I change the slope and the intercept a little bit. Okay? I'll experiment with that a little bit more next time. But again, you should do the same kind of stuff in this spreadsheet here, and I'll share that with you. Download it as Excel. Use one of the school's computers if necessary, and upload it back on Moodle. By the way, I just went to a parent-teacher conference last night, at my kids' high school, Moms Youth, and they're using, instead of Moodle, some classes are using Google Classroom, which sounds easier because you don't have to download it and then re-upload it. But we're using Moodle at the moment. All right. Got a lot to do here in the last little bit of time here, so hang on to your seats. Important stuff to talk about. I was going to talk about making some diagrams for experimental design. Going to skip that. There are plenty of examples in the book. You've got a problem or two where you've got to make a diagram, like you'll find in the book, for how an experiment is designed. Just mimic the book's examples. Okay, it's not too hard. What I want to focus on here, though, let's see, starting right here, are some really important things. Populations and parameters versus samples and statistics, first of all. We've talked about populations and samples before. Haven't talked really in depth so much about what parameters and statistics are. I mean, you have an intuitive idea of what a statistic is. It's a numerical summaries or statistics, for example. But the focus is a little different here. You may want to write this down for extra emphasis. A parameter is a number that describes a population. A parameter is a fixed number, but in practice, almost always, we do not know its value. Contrast that with a statistic, which is a number that describes a sample. The value of a statistic is known when we have taken a sample, but it can change from sample to sample. We often use a statistic to estimate an unknown parameter. Pretty much every word, including the uhs and thes and ins and buts, is really important here. Okay? These are really, really super important definitions. We've already said what a population and sample is. A population is the whole, the entire set of individuals you want to know information about. A sample is some subset of that. How you pick the sample matters. We typically are going to assume we're doing simple random sampling, even if in practice that's difficult to do. That's what a population and a sample is. Now we've got two new words, parameter and statistic, at least two new uses of these words. It's very fortunate that the P's go with the P goes with the B, and the S goes with the S, okay? That's great, a great coincidence in English. I don't know about other languages, but in English it's a great coincidence. Parameters go with populations, statistics go with samples. I can't emphasize enough, parameters are fixed numbers. At least you imagine them to be fixed. There could be some debate sometimes about that, but you imagine them to be fixed. That you don't know, and you'd like to know, you'd like to estimate. That's the goal. Statistics are numbers that you can calculate based on the sample. Assuming you don't make math mistakes, you get a value. I can't emphasize enough, it can change from sample to sample. If you took a different sample, you get a different value. Which only makes intuitive sense if you think about it. If I'm measuring people's heights, ignoring measurement error, if I pick one group of people, I'll get a certain mean height, and I pick another group of people, I'll get another mean height. I'll get a different answer. Pretty obvious that that happens, but it's super important, and people forget it all the time in this class. Statistics are not constants. They depend on the sample. They're really variables. And as variables, as what are called random variables, in fact, they're going to have what we call a sampling distribution. And we often use a statistic to estimate or predict an unknown parameter. That's why we use statistics. This is the heart of inferential statistics, trying to take information about the sample and infer information about the population, make predictions or estimations. All right? Super, super important. You've got some problems where you take some situations and you have to identify the population, the sample, the parameter, the statistic. In most cases, the population parameter of interest is unknown and too hard to precisely determine. So instead, we take a good random sample, a simple random sample, ideally, for us at least, from the population and use the sample statistic as an estimate for the population parameter. The big question is, how do you know if your estimate's any good? I should say that's another big question. How do you know if your estimate's any good? If I measure basketball players' heights, that's probably not good to estimate the true mean height of everybody. Not a good idea. That's a biased sample. You want to avoid bias if your information is going to be any good. One way to do that is with random sampling and asking how trustworthy the procedure is if we repeat it over and over again many, many times. All of statistical inference is based on one idea. To see how trustworthy the procedure is, ask what would happen if we repeat it many, many times. So we're going to imagine repeating our sampling many, many times over and over again. You want it to be random sampling. That's going to lead to what's called unbiased estimators. Estimators that don't tend to overestimate or underestimate the actual parameter values systematically. Typically about half or above or half or below. That's not quite our correct description of a skewed distribution. And you also ideally want your sample to be bigger. If you pick a sample of size 1 and you happen to pick a basketball player, even if it was chosen at random, that's not going to give you a good estimate for the true mean height. So pick a bigger sample. You might still get a basketball player, but you'll also get shorter people too if you take a bigger sample and you're doing random sample. So that the extremes kind of get averaged out. Can't emphasize how fundamental all these things are to really getting statistics. We're going to be thinking about these ideas over and over and over and over and over again in the coming months in different situations. This is the key to getting everything from this point on. There's variability. When we repeat the process of obtaining a statistic from a random sample over and over again, we will get different values for different samples. The accuracy of the estimate can be described by something called the sampling distribution. And the two main characteristics we look at the sampling distribution are that are especially relevant. bias and variability. You don't want bias. You want it to be unbiased. And you want low variability. You can't get rid of variability completely. It's impossible in practically every situation. So the variability is going to be there, but you're going to want to make that low by taking a bigger sample size, as long as you're doing the random sampling. The random sampling is what gets rid of the bias, makes it unbiased. And when you're doing that random sampling, if you take a bigger sample, that'll reduce the variability. The extremes will get averaged out more, in a sense. Right? And different samples will produce different values, but they won't vary by as much. They'll be close together, relatively speaking. We desire the sampling distribution to be unbiased and have low variance, low variability. Bias concerns the center. The statistic is unbiased if the mean of its sampling distribution is equal to the true value of the parameter being estimated. And the variability of the statistic is described by the spread of its sampling distribution. This spread is determined by the sampling design and the sample size. Though again, for our simplest kind of sampling design, simple random sampling, you really only need to worry about the sample size for the variability. Statistics from larger samples have smaller spreads. Okay? I'm going to draw some pictures on the board here now to try to illustrate these ideas, and you really need to think hard when I draw these and describe them, what I'm talking about. Here's a common situation. Let's go ahead and think about heights. Okay? Let's say we want to know the mean height of all females at Bethel, female students at Bethel, in your age group. So we're talking about your traditional undergraduates. It is traditional to call that mean mu instead of x bar. And this is analogous to the fact that we called means of sampling distribution, of density curves mu as well. Isn't this great? This Greek letter mu, it kind of looks like an M, it kind of looks like a U, and we call it mu. Isn't that great? Mu. Funny looking thing, that's the mean that we're after. Mean of the population. It's an assumption I'm making with the heights that at any given moment in time, that's a fixed number. That all the women students here at Bethel have a certain height at any given moment in time, and that mean exists. There is some average height. Now, is it really constant? Could it change a moment later? Well, theoretically, it probably could. Somebody's growing a little bit, even over a few seconds. You know, we're talking about microns of growth. Maybe you lose a cell on the top of your head, a hair falls out that was sticking up higher. Okay, tongue in cheek here. You know, we're assuming it's constant. X bar would be the mean of the sample. So I randomly pick 50 women students in your age group here at Bethel, measure your heights, and then take the average, the mean of the sample. Assuming I can measure perfectly, which I can't, that can certainly be calculated precisely for that sample. But if I picked a different sample, I'd get a different answer. So which one's right? Probably neither one, in all likelihood. However, if I pick people at random, and if the sample size is large, 50, it's moderate size, I should expect them to both be close to each other, relatively speaking, and hopefully both close to this. I'm going to draw a normal curve. Normal curves never go away in this class. They're always there. What is this normal curve supposed to represent? This is supposed to be a picture of the sampling distribution of the statistic, of x bar in this case. What does that mean? It's supposed to be a model of the histogram you would get if you sampled from the same population 50 women over and over and over and over and over again. So I pick 50 women, I measure their heights, I take the average. I pick 50 more women, I measure their heights, I take the average. I pick 50 more women, I measure their heights, take the average. Over and over and over again, hundreds of times. I get a bunch of different values for X bar. I can make a stem plot, I can make a histogram. The histogram, I'm claiming, would look like a normal curve. This is supposed to be a model of that. The fact that I'm doing random sampling is going to mean this is unbiased, which is going to mean the center of this, the mean of this sampling distribution, which I'm going to label mu sub x bar, weird, mu sub x bar? Yeah, because it's the mean, the theoretical mean of the sampling distribution of x bar should be the population mean, the true mean that I want to know. The true mean height. Now you scratch your head and say, well, if I don't know that true mean height, how can I know that it's going to be centered there? This is all theoretical. It's supposed to be centered there. And based on some assumptions, like simple random sampling, you can in fact prove this is true with abstract reasoning. We're not going to do that abstract reasoning. That's for an advanced course. But based on assumptions like simple random sampling, even though you don't know what this number is, you can still prove the sampling distribution is centered there. Doesn't mean your histogram will be centered there, because this is a model for the histogram. But the theoretical sampling distribution will be centered there. And have a certain amount of variability measured by whatever that distance is. Maybe you want to call that sigma sub x bar. In fact, I'll go ahead and go to the punchline. The formula for sigma sub x bar is sigma divided by square root of n, where sigma is the standard deviation of the population of heights in this case. The entire population, n is the sample size. I divide by the square root of the sample size. Which will get smaller as n gets bigger. That's the real point I was trying to make by writing that formula. This gets smaller as n gets bigger. Bigger samples lead to smaller values for this, leading to skinnier and taller sampling distributions. And as long as you're doing random sampling, leading to more tightly clustered x bar values that are closer typically to mu. Here's a nice little visual. Like target practice. Now that's the ideal right down there. Ideal is small bias, small variability. Variability means you're consistent. Small variability means you're consistent. Small bias means you're close to the center. What's the worst one? I guess that's the worst one. Large bias, large variability. The points are more scattered, that's a large variability. They're far away from the center. The bullseye, that's a large bias. But you can have a lot of variability yet still be unbiased. Okay, these are pretty much centered on the bullseye, but there's a large amount of variability. You can also have a large bias and small variability. You're consistent there, but you're consistently away from the bullseye. This is the ideal right there. You want a small bias and small variability. You want to hit the target, hit the bullseye, consistently. To reduce bias, use random sampling. Simple random sampling produces unbiased estimates. This picture that I drew will be true. It will be centered where you want it to be centered. When you do the simple random sampling. For more complicated kinds of sampling, then it gets more complicated. The math is easiest for simple random sampling. That's why we talk about simple random sampling, because the math is easiest. Doesn't necessarily mean simple random sampling is always practical or always the best thing to do, actually. It's just the math is easiest. So we focus on the things that give you the easiest math in this class. If you want more complicated kinds of sampling techniques and what to do with the math for those, you take like a graduate level class in statistics. To reduce variability, use a larger sample, make n bigger. You can make the variability as small as you want by taking a large enough sample. You can make this number, no matter what sigma is, you can make that number as small as you like by making n sufficiently big. Which if you've ever taken calculus is related to limits. If you haven't taken calculus, you don't have to worry about that. Population size, it turns out, does not matter In most situations, the variability is basically determined by the sample size, not the population size. At least when your population is at least 100 times larger than the sample, that's just a rule of thumb. Does that typically happen? Actually, it does typically happen. Usually the population is a lot bigger than the sample. Sometimes you might even say the population is infinite. To end class today, we're going to look at Table B again and look at one of your homework problems. Got about 1 or 2 minutes here. No, actually 3 minutes. The homework problem I'm thinking of, is problem 3.86. It's on page 190. 3.86, page 190. If this is a future class that doesn't use the same book, this still might be beneficial for you to hear about. In this problem, you're going to use this table of random digits to do something, to do a simulation essentially. You're pretending you happen to know the population parameter. In this case, the population parameter is that 60% of the population ate at a restaurant in the past week. You're pretending that's known. That's usually not the case. Usually you don't know the population parameter. Usually you want to estimate that. In other words, the population proportion, the fraction of people who ate at a restaurant in the past week is 0.6. What do the directions say? Part A says, use each digit in this table to stand for one person. So each number besides the line number stands for one person. Digits 0 through 5, 0, 1, 2, 3, 4, 5, 6 digits represent people who ate at a restaurant in the last week. And digits 6 through 9, 6, 7, 8, 9, 4 digits represent people who didn't. Why does looking at one digit from table B simulate drawing one person at random from a population of equal to 0.6? It's because there's 6 digits that are 0 through 5. 0, 1, 2, 3, 4, 5, 6 digits. 60% of the digits, 0.6, 6 out of 10. And because it's a table of random digits, and because each digit represents one person. For all those reasons, looking at one digit represents drawing one person at random from a population of p equals 0.6 percentage or fraction of people who ate at a restaurant in the last week. Look at part B. The first 100 entries contain 63 digits between 0 and 5, excuse me. Why do the first 100 digits represent simulating from 100 people at random? So let's see, 5, 10, 15, 20, 25, 30, 35, 40 in each row. The 100th digit comes to right there, it looks like. So the authors looked at those first 100 digits and counted how many were 0, 1, 2, 3, 4, or 5. And got 63 of them. 63 out of 100. 0.63. For their statistic value for their sample. And this simulates sampling 100 people from this population because this is a table of random digits and because each person is represented by random digits. In part C, you are supposed to do a similar thing. Simulate a second simple random sample by using 100 entries starting on line 114, right there. So you will look at these 100 digits here, count how many are 0 through 5, write the corresponding fraction, and write it as a decimal. That is another value of the statistic of sampling from this distribution, or from this population, and getting a percentage of people who ate at a restaurant in the last week based on a new sample. It should be a different answer than the book got for B, most likely. Okay? I'll let you finish that. See you next time.